Adapt Mat 2009 is foundation design software utilizing true three-dimensional solid modeling for mat foundation and grade beam systems. Multiple soil properties can be modeled for the same foundation. Also, modeling of complex geometries including varied slab thicknesses, steps for both foundations and grade beams, openings, and columns and walls can be modeled at any location. Build 4 of Adapt Mat 2009 also includes 20% faster meshing, analysis, and design time leveraging multi-core processing. There are new and improved component visibility controls. New Tendon Modeling Manager allows the ease of showing profiles and force for any tendon, and the lateral load input has also been improved. This tutorial will cover the basics of designing, analyzing, and completing a design in Adapt Mat 2009. To begin, we're going to open Adapt Builder 2009. We want to make sure that the modeler is checked under structural modeling. We also want to make sure mat and raft foundation is checked, along with the design scope set to RC only. For this particular tutorial, we're only going to work with a mild reinforced slab. We also want the dynamic rebar design or DRD turned on, and we can leave the import-export options turned on as well. We'll use the American system of units, and we'll select OK to begin the design. To begin modeling the structural components, there are a few different ways to do this. The first is we could go to Build, Structural Components, and we could begin adding regions like slabs or columns or walls. Another option is to import a DWG or DXF file. Go to File, Import. We'll select the DWG. We're going to select Mat, PT. It then asks us if we want to calibrate. We'll say yes. And this just allows us to scale the drawing to the correct size. We're going to select two known points. We'll enter the dimension in feet between those points. So this is 30 feet. It then asks us if we want to change the origin. We'll say no. And at this point, we can go ahead now and start creating the model. We can either trace the different objects, or if they're enclosed polygons, we can also transform those objects into structural components. We're going to use this tool here called the Layer Settings tool to manage the display of some of these lines and objects. So the first thing we want to do is we want to turn off each of the layers except for this layer for the slab region. If I double click on that layer and I go to Properties, I can see that it's called Edge of Slab, so that's the layer that we want to turn on. I'll go ahead and close that. Open Layer Settings. I'm going to turn all the layers off, and then I'm going to scroll until I find Edge of Slab. This is a layer that I would like to turn on, so we'll select that layer and say OK. And now we can see that I have a complete layer here. The next thing I'll do is using the Build toolbar. I'm going to say Build, Structural Components, Slab Region, and I'll simply trace this region. Now in these regions where the slab edge is curved or arced, we're going to use this Snap to Nearest, and we can essentially use straight segments to model that region. The same for the other side. We'll be using the Snap toolbar quite often, so I'll leave that toolbar on during the duration of the model. Once we're finished, we can press C on our keyboard to close that region, and we'll exit. We'll notice that here I have to shift this slab point to the corner, so if I click on the slab, and I can grab that handle and just move it over with my snap tools. So that's been moved. So this is the first slab region that we've created. Now I'll go back to Layer Settings, and I want to turn all of my layers on again. We'll select OK. The next thing we're going to do is we're going to assign a thickness to the slab that we just created. So here we can see that this is a 20-inch normal weight concrete slab, 5 KSI. We're going to select that slab. Using the Item Properties menu, we can select that, and for the thickness we're going to say 20 inches. Select OK by the green check and close out of that box. And now we're going to include this 24-inch thick mat that's in the middle of the slab. So I'm going to leave all of my layers on here, and again I'm going to go to Build, Structural Components, Slab Region. I'm going to set my thickness to 24 inches. Notice that the top of slab is flush, so there's no vertical offset. And I'm going to just begin to trace over the lines shown on the screen. I'll start here. And if I click along this slab that's already been defined, you'll notice that the program is finding the different points of those segments that were created, so I can match the slab exactly as it was created the first time around for this arc. And that was a mistake. That's okay. I can just go over to this point, to there, and then back to this point. And again, I'm just creating the edge of the slab by using the endpoints. And then we'll say C to close that slab. And again, you'll notice here I click the point in the corner. It should be this point here. So I can highlight that slab, I can grab that end and just shift it over to the point where it needs to be. Once that's finished, I'll press C to close. And to verify that the slabs have been input correctly, we can use the section tool to look at that. I want to go to User Interface and open the Modify Selection toolbar. And we can use this section tool here. If we click on that, and we click on two known points, so I'm going to click here and here through the step in the slab, and then I click out here in some white space. We notice here that we have a thickened region that's 24 inches, and then there's a step on the soffit side up to 20 inches. So the slabs have been input correctly. We can go ahead and exit that. We can just delete that section. And then the next step we'll take is we're going to transform the columns, these closed polygons, into actual structural columns. So I'm going to go back to Layer Settings, turn off all of the layers, and I want to turn on the columns only. We need to go ahead and verify which layer that is. So I'll turn back the layers on. Let me just double click on a column. Close that. Turn that layer on. Now if we select all of these columns at once, we can transform those into structural components. So if we go to the User Interface, or we can go to Build, we can go to Transform Drawing Entities. We're going to transform these entities into columns. Once we've done that, those columns have been created. We'll go back to Layer Settings. We're going to turn off all of the layers, and then we're going to turn on the slab edge. That's the slab region, and we're also going to turn on the columns. We'll say OK. And now we have a structural model including the slab and the columns. For this particular model, we're going to arbitrarily select an opening in the slab that represents the opening for an elevator pit here in the middle of the structure. So we can just use the Build toolbar. And if we go to Structural Components Opening, We're just going to select 4 points near the middle of the structure. So we'll select here. Using the orthogonal tool, we can select straight points and there. And we'll say C to close. If we want an overall three-dimensional view of this structure, we can use the viewing options for this. So we can turn this on, top front right view. That will show us an isometric view of the structure. We can go ahead and go back to the top view. And for a three-dimensional rendered view, we can select the view model. This allows us then to see the completed geometry for this particular model. The next step in the modeling process is to include the area spring acting as a soil support for the slab. To do this, we're going to go to Build, Spring/Soil Support. We're going to add a soil support. And then in the Item Properties box, we're going to make sure that it's compression only. And in the Z direction, we'll use a K value of 100 pounds per cubic inch. We'll select OK. And now we can go ahead and we can just define the boundary that this soil support will be applied to. So we'll select the different corners of the slab. Note that you can also include a region that simply envelopes the entire slab boundary. It doesn't have to be on the edge of the slab. For this model, we're inputting it at the edge. Once we're done, we can exit, and then if we go to a three-dimensional view, we can see that the soil support is shown by these zigzag lines. If we double click on that, that will open the properties box and it shows us the spring constant we've selected. We can close that. We'll go back to the plan view, and now the soil support has been added. Note that for other types of systems, if we go back to Build and Spring Soil Support, we can also include point springs and also line springs. Those might act as grade beam supports like piles, or pier caps with piles and so forth. Now that the springs have been added, we're going to close this toolbar and we'll begin to load the structure. So I want to turn off the display of the spring. I can do that by going to Select Set View Items, and under the Finite Element Components, we'll turn off Soil Support and say OK. And now we get the slab with the columns and the opening. Now to load the structure, I want to turn on the loading toolbar, so we'll go back to User Interface. We'll select Loading Toolbar, and I want to select the entire slab region. Using the Patch Load Wizard, this icon here, we'll select that. And for dead load, we're going to use 10 PSF, so we'll say 0.01 KSF. Press Enter to create that. We're going to select the same region, and we're going to have a live load of, let's say, 40 PSF or 0.04 KSF. Again, if we review the three-dimensional display and turn on the loads to display, we can see that the loads have been added. So if I double click on either of these loads, we can open up the properties box, we can see the magnitude, the load case that it's been assigned to, any group assignment, and also the label. We can also put in a variable magnitude. There's additional loadings here that we can input, as well as the location of the load, and also the properties, which layer that load is on. The same can be said for the dead load. If we double click there, we can see that there's 10 PSF assigned as a dead load, and again the same information can be found in the property box. Using the display items, here if we go to loads, we can also display these loads and control their display using this selection. So for patch loads, we've only input patch loads. We can turn off the dead load or the live load, and we can display those individually. So we'll leave those both on. I'm going to turn the loads off again, go back to my plan view, and for this interior slab we're going to add additional live load. The live load will be superimposed, so we're going to use another patch load wizard, and here we're going to add 20 additional pounds per square foot of live load, so we'll say 0.02 KSF. And now if we go back to this view and display the loads again, we can see that the live load of 40 still applies, but now we have an additional 20 PSF of live load on the interior slab. So that looks fine. We'll go ahead and close the display. We'll go back to the plan view, and now the slab has been loaded for the area loads. Now that the area loads have been added, we want to add the point loads at the columns. For the 5 exterior columns at these corner boundaries, we're going to include 30 kips per column. At the 2 interior columns, there will be 70 kips per column, and at these 4 columns near the arc for either side, there will be 15 kips per column. To do this, we're going to use the point load tool. We'll select that. For the properties, we're going to change this to 30 kips and this to live load, and we'll just begin to add these exterior columns. We'll right click and press exit, and we'll do the same command. We'll do the 2 interior columns. This will be 70 kips. And now we'll do the additional 4 exterior columns, which are 15 kips of live load. Now note, for these columns we're only including gravity loads with no moments. So to include a moment, you can simply double click on the load. If you have a moment to add that's a live load or the same load case, you can add that here for the X or the Y direction, or you can add that individually if it belongs to a load case like wind or earthquake. Again, we're going to go ahead now and we're going to add the dead loads to these particular columns. So what I want to do is I want to turn off the loading for the live load. If I go to Select Set View Items and Loads, I'm going to turn off live load and leave dead load turned on. And now I can go ahead and add my dead load. And for the dead load, we're going to use 75 kips for each column. That will be interior. For the exterior columns, we're going to use 40 kips. And again, for the 2 exterior columns near the arcs, we're going to use 20 kips for dead load. And if we want to review these, we can again double click on the load. Notice here that these were assigned as live load. We need to change those to dead load. And now the loading has been completed in the model. We can also review this going back to this 3-dimensional view, and we can see the loads input at each of these columns. We can click on those as well to review. In this display we're only showing the dead loads. If we only want to show the dead load for point load, we can turn that on or off for either of these load types. So we're going to select both loads with point and patch, which have been assigned to the structure, and so this is the entire loading on the structure to this point. This will also represent the final loading for the structure. So we're going to go ahead and go back to the plan view. We're going to turn off the loading. We now want to review the different load combinations that we have in this model. So to begin, we're going to set the code type under Criteria. Design code, we'll use HCI 2005, IBC 2006. Select OK. In loading, under Load Case Library, the default load cases are dead load and live load. Again, if you want to add any additional load cases like wind or earthquake, you can simply do that by adding here, and then you can assign point loads, line loads, or patch loads to that particular load case, as we did before. We'll select OK. If we go back to loading, under load combination, we want to review the different load combinations that we have. We have service total load, which includes 1 times the self-weight plus 1 dead load plus 1 live load. We have a sustained case where we have 1 times the self-weight and dead load and 0.3 times the live load. And then we have 2 strength cases, which is strength dead and live, which includes 1.2 self-weight and dead load plus 1.6 live load. And strength dead only would be 1.4 self-weight and 1.4 dead load. We're going to also include a case with only the self-weight so that we can use that to verify the model. So to do this, we want to change this label, and we'll write in self-weight. Notice that the warning comes up that we're unable to use that because that's the actual name of a load case that defaults, that the program defaults to, so we'll just change this to SW. In the combination parts, we're going to delete dead load. We're also going to delete live load. And for the analysis design options, we're going to select no code check. This will just be to look at the results so that we can validate the model. Under self-weight, we'll say save, and that gets added to the combinations list. The rest of the load combinations look correct, so we'll select OK. And the load combinations have now been created. We're now going to set the material properties and the criteria for this model. So under material, we're going to go to concrete. For normal weight concrete, we'll use 150 pounds per cubic foot as the unit weight. The unit price is valuable if you're trying to extrapolate some results for the cost per cubic yard of concrete. We'll leave that as it is. Under the cylinder strength for mechanical properties, we'll set the compressive strength to 5,000 psi. The modulus of elasticity will update automatically, and the rest of the information we'll leave alone. So we'll say OK. Going back to material, we're going to select mild steel. For the yield strength of the steel, we're going to select 60 KSI, so that's correct. The modulus we're going to change to 29,000 KSI, and for the unit weight and the label we'll leave alone and select OK. We'll now go to criteria. Criteria, there are several different options to choose from. Notice on the left hand side there are 3 options for two-way slab, one-way slab, and beam. These are the different criteria that you can select for the design of a support line. For this particular slab, we're going to be using two-way slab criteria, so we'll leave one-way slab and beam as the program has defaulted to, and we'll go back to two-way slab. We've already selected the code, that's okay, so we'll just go through systematically now for each tab and put in our criteria. For reinforcement bar lengths, we're going to leave the minimum bar length cutoffs as they are, and also the extension of reinforcement beyond 0 moment. We'll go ahead and change that to 2 feet or 24 inches. For bar length adjustment, we're not going to select any of these options at this point. Under rebar minimum cover, for a mat slab, we're going to use 3 inches for top bars and 3 inches for bottom bars. For the rebar roundup and spacing, we're going to leave the bar roundup to 6 inches and the spacing round down to 1 inch. And also for bar spacing, for the bar maximum spacing, we'll leave that as 18 inches and we'll leave this as 1.5 inches. There's also an option here to include a library length, so when the program generates rebar, it will round up bar lengths to these particular sizes. We're going to leave the default library as it is. We're going to go back now to Analysis Design Options. In this part of the program, you have the option to select things like General Analysis and Design Options. Since we don't have any beams, this is going to be a regular floor or mat system. We're going to leave these settings as they are. We're also going to leave the support conditions as the program has defaulted to, which is a fixed roller condition. For conventionally reinforced only concrete, we're going to select No to column middle strip. We'll base our design strips off of the full tributaries between columns. We are going to use minimum reinforcing, and we're going to consider 100% of the torsional stiffness for the beams and the upper columns. There are no beams, so that does not apply in this case. We're also going to select this option to generate the design section moment capacities. If this option is not selected, these capacities will not be reported or generated for a tabular report. For the mesh type, we're going to use a sparse mesh rather than a uniform mesh. And lastly, we'll go to preferred reinforcement size. We're going to use number 6 bars for top and bottom, mild still of 1. That's the mild still that was input and defaulted to. And for shear design options, under two-way shear reinforcement, we want to select 1/2 inch diameter studs, 2 rails per side, and for the design we're going to look at each side separately. We'll select OK, and now we're ready to mesh the structure. To automatically mesh the structure, we'll go to FEM, and using the automatic mesh generation feature, we'll select that. The default sizes are 3 feet, and also the node consolidation is 1.5 feet for the maximum distance. For a cell size with a 20 inch or more thickness, we can actually use 4 feet here, and since our slabs are 20 and 24 inches, we'll go ahead and change this to 4 feet. The node consolidation value should be no more than 2 to 3 times the slab thickness. In this case, we're going to go ahead and set this to 2.5. We'll select OK and continue here, and the mesh will be generated automatically. There's also an option to manually mesh the structure. If we go back to FEM and use this option, we can manually mesh different segments within a structure. We could select this. We could select the number of the first side and the second side, and the program will automatically generate the manual mesh that you've selected based on this criteria. We'll go ahead and cancel that. Now that the mesh has been included, we can begin the analysis process. So we'll go to FEM. We're going to go ahead and analyze the structure. We'll select Yes for the confirmation, and the program will begin the analysis. Once the analysis has been completed, we'll go ahead and say yes. And now we can go ahead and view the analysis results. These are preliminary results based on the self-weight only. We're going to go ahead and turn off this shell display. So if we go to Select Set View Items, under Finite Element, we can turn off the shell cell element. And that will default back to the main plan. To view the results, we can go to FEM, View Analysis Results. The first thing we want to do is we want to change the load case and combination to self-weight. Notice that results are also generated for all of the combinations that were created by the program or that were user specified, like self-weight. In this case, we just want to look at self-weight, go back to the Results tab, and the first thing we'll look at is the deformation or deflection in the Z direction. We'll select Z translation. With the color contour on, we want to go ahead and display the results. So we'll select this. And this is now the contour for the displacement under self-weight only. We can see the scale here shows us that we have around 0.02 inches maximum. We can also review that three-dimensionally by holding down the left button on the mouse and moving the mouse to whatever position is acceptable. We can warp the view to get a relative check of the displacement. We can see that the maximum displacements occur out on the edges of the perimeter beam or the perimeter columns where we have the heavy loading. Note that positive values of displacement are downward and negative values are upward. So once the displacements look satisfactory, you can go ahead and we can check the soil pressure based on self-weight only. If we select soil pressure here, we now get the contour for the soil pressure and the appropriate values. Negative soil pressures mean that the soil is reacting upward. So for the maximum here we have negative 2.43 times 10 to the negative third. This is reported in KSI. So in order to convert that to PSF, we would multiply by 144 and then by 1,000. So based on this particular model with the loading and the soil stiffness, we get about a soil pressure of 350 pounds per square foot under self-weight only. You can also review things like slab actions. We can look at moments about the x-axis. We can look at moments about the y-axis, moments about the xy or twisting moments. We can look at axial loads in both directions or in-plane shears. We can also look at column actions like axial force, we can scale those up or down and also show the values. We can look at moments about the y-axis. This is a local axis in the x direction, and the b-axis, which is the local axis in the opposite direction. Here there are no moments applied, so we'll have no moments reported. And we can also see torsion for the columns as well. Once you've reviewed the different values in the results viewer, we can continue with the generation of design strips and continue with the design of the structure. The next step in the design process will be to include the support lines necessary for the creation of design strips and also design sections. The design sections are where the program evaluates actions such as moments, axial loads, shears, and so on for the design of reinforcement or for the check of stresses in the slab. We're going to go to User Interface and select the modeling toolbar. Using this tool, we're going to create the support lines. We want to change this to X direction. And along each column line, we're going to input a support line. We're going to start at the slab edge and go from center to center of column. Notice that the snap tools that I have turned on are snap to endpoint and snap to nearest. For this direction, the X direction, we're going to include support lines over these columns. We're going to go to about half the span between these two columns, and we're just going to terminate the support line there. And we'll do the same in this direction. This is one option to include these columns in the design. We could ignore these columns, but then the tributary would just be between these two support lines. The program would split the design strips between this support line and this support line. Because this support line stops in the middle of the slab, we need to add an imposed boundary, also called a splitter, in the program. We can go to the Create Splitter tool, make sure that this is in the X direction. We're going to turn on the snap to perpendicular, and we're going to create these splitters here. We'll do the same for the support line towards the bottom of the slab. Once those have been input, the support lines in the X direction have been completed. We're going to go ahead and maximize the view, and under Select Set View Items, we're going to turn off the X direction for support lines and splitters, and we're going to turn on the Y direction. We now need to input the Y direction, so we'll go back to the Create Support Line tool, change the direction to Y, go Snap to Nearest, and we'll do the same type of input as we did for the X direction. When I terminate the support line, I can either press the C on the keyboard, or I can right-click and I can close to accept. For this direction, we're going to use an alternate approach to including these columns in the support lines. One could argue that the support line would go from this column to this column, considering that it's a shorter span than from here to here. So we can take the support line, again this will be in the Y direction, and we can go from this column to here and then to the slab edge, and we can do the same on the opposite side. Once our support lines in both directions have been included, we can exit. We'll close the modeling toolbar, and now we can generate the design strips for FEM. If we go to Strips, Generate Design Strips for FEM, the program will generate the design tributaries. Notice here that this opening has been included or excluded from the design strips in each of these directions. The program can automatically detect the opening, and it will apportion the design tributary to each of the support lines correctly. If we want to review these design strips, we can then go under Select Set View Items, and we can now toggle to the X direction. Under User Interface, we can open the Report Plans toolbar, select the X direction, and we can see the different design strips that have been created by the program. We'll do the same for the Y direction. After these have been reviewed, we can close, and we'll continue with the design. To continue, we need to generate the design sections along each support line. We'll go to FEM, and there are two options. We can create the design sections manually. If we select this option, we can just select 2 points, and we can populate the slab with as many design sections as we would like. We'll go ahead and exit and delete those sections. The other option is to have the program generate the design sections automatically. We're going to use this option for the design of this slab. The program has now created design sections along each support line. To view these, we're going to go to Select Set View Items. We'll turn off the tributary regions, and we'll view the different support lines for each direction. We'll go to X first. Here we can see that this black line or red line represents the design section along each span for each support line. So here we have 6 separate support lines. We'll now go to the Y direction. And here again we have 6 separate support lines. For each of these support lines, the program will determine the actions at the centroid of the design section, and the program will then design reinforcing for those actions. To begin this process, we'll go back to FEM, and we'll select Design the Design Sections. The program will then begin the design for each design section. Once the design is complete, we'll select Yes. We'll note that all the design sections for either direction will turn green. To toggle between the different directions X and Y, we can go to User Interface. We'll open the Model Design Strips toolbar, and now we can toggle between the Y and the X direction. If we want to view results like moments, shears, and so forth, we can go to User Interface. We'll select the Support Line Results Scale toolbar. By selecting the Result Display settings, we can toggle between the envelope or any of the load cases that have been populated for the program. Here we'll select Self-Weight. The action we'll select as Bending Moment and we'll apply. We're also going to turn on the option to display graphically, and here we can see that the program will generate moment diagrams for each support line. Those can be scaled up or down. We can also view the results at each different design section. Here we'll need to adjust the font height, so we'll go to Select Set View Items, and we can change the font height to 8 inches under Support Line. And now we can read those values at each design section. This is again is the moment diagram for self-weight. We can also review diagrams such as the shear normal to plane, axial load, moment, axis normal to plane, and bending moment in plane, and also torsion. We'll go ahead now and turn the moment diagrams and the shear diagrams off. Another option within the Support Line Results Scale toolbar is to check the punching shear. So we can go ahead and select this option once the punching shear has been run under FEM. We'll go to Punching Shear Check. The punching shear has been completed successfully, the check for that. We'll go back to this option, and here the program will report the stress ratio for the R and the S direction. Those are the local axes for the columns. Notice also that the program shows the status of each column. Here it says OK. If we select 1, 2, 3, it will only show the status. Now that the punching shear has been completed, we can go ahead and deselect that. We're also going to turn off the display design sections, and we're going to close this toolbar. And we'll now go ahead and we'll generate the reinforcement for both the X and the Y directions at the top and the bottom. To do this, we'll go to FEM, Generate Rebar Drawing. In the Generate Rebar options, we can select any load combination or envelope. We'll select envelope. For bar length selection, we're going to select the calculated length as compared to the library lengths. And for the bar orientation, we're going to use the orientation along support lines. We'll select OK. A warning will appear stating that the bars shown in blue cross between two different thicknesses of slabs. Therefore, their orientation or their placement needs to be respective of each of those slab thicknesses. We'll select OK, and now the rebar is shown on plan. To isolate individual layers or individual directions for rebar, we can go to User Interface, make sure that the reinforcement toolbar is displayed, and we'll go to Open Rebar Display Options. We'll first display the rebar in the X direction along the bottom. We'll select OK, and now we can display the rebar shown at the bottom of the slab in the X direction. Here we can review rebar, we can change rebar, or we can manipulate the bar size and spacing. For example, if we select 21 number 6s by 23 feet at 17, we double click, we have several options. The first is we could change this rebar to base reinforcing. This means that the program will store this amount of rebar for the model, and if additional loading or any other model changes are made, this rebar will stay in the model. If the program and the analysis is run again, this rebar will be used as base reinforcement, and any additional reinforcement required will be added to this rebar and shown separately in the display. We can also change the placement and grouping of the rebar from bottom to top or vice versa. Here we can change the rebar size. For example, if we want to change this to number 8 bars, we can select that and notice in plan that change has been made. We'll go ahead and change that back to number 6s. Notice also that the extents change depending on how many bars are required and the spacing. We can change the number of bars required by making sure this is selected to fixed. Let's say we want to use 24 bars. We select the green check. Notice that the spacing changes. We're going to go now and change that back to 21, and the spacing changes again. If we select to fix the spacing and deselect the number of bars, we'll go ahead and change this to 18, press the green check, and again the number of bars is updated. On plan, you can also change the orientation of the bar by simply clicking on the bar. We can grab one end and we can move it in any direction we would like. Notice now that the bar number, quantity, and the length changes according to what the user input. We can go back and change that to straight. You can also review the Y direction or the other layers using this tool and selecting it from the rebar along the X or the rebar along the Y. You have the option to display the top or the bottom mesh reinforcing if that's input into the structure, and also you can display the required and the provided rebar along support lines. If we want to do this, we'll select OK. We'll open up the X direction support lines and select any support line, and we'll select each of these options. And now we can see the solid black line represents the envelope of provided rebar, where the black tick marks represent the quantity of required rebar. The user has the option to input mesh reinforcing either through the use of a wizard or manually. You can also manually create distributed or banded rebar. This is particularly useful for the design or the analysis of existing slabs where a known quantity of reinforcement can be provided. Once the rebar has been checked and the final design has been validated, you can send this rebar to a CAD drawing by going to File, Export, DWG, DXF. Here you'll be able to select the different version of CAD associated with your design, select OK, and you'll then be able to save the file. You can also review results using the Builder Sum. If we select any support line, open the yellow tab, Builder Sum will open. Here we can drop down to any load combination or envelope. We'll select envelope. If we select the design summary, we can see the reinforcing top and bottom, the required versus provided, and any notes provided by the designer. We can do this for any load combination as well. We can also review the rebar individually. We can review the bending moments, the shear forces, or we can export the graph for print. The last option to review results is through the tabular format. Under Reports, Single Default, we can go to Tabular, and here we can select Design Section Data and select Design Section Rebar Tabular Report. Here we can select any of the load combinations or a group of the load combinations, and we can envelope those combinations. We'll go ahead and select Strength, and we're going to generate the envelope excluding the selected cases. We'll say OK, and a Word document will then open with this particular tabular data. Once the Word document is open, we have a tabular report showing the support line. This is again the envelope of the two cases that were selected. we show the rebar at each design section for service, strength, and the rebar selected for top and bottom, and then the number and quantity of bars. This is populated for each support line. Also note that the shear reinforcing is also shown for this slab. Here it's not applicable. Those reports can be generated for any combination of load cases or for the total envelope. Reports can be generated for several design options or analysis options. If we go back to single default reports, Tabular, we can create reports for structural geometry, material and design criteria, analysis data, a report showing the load cases and combinations, design section data including the design section forces, rebar as we just looked at, moment capacities, the design section dimensions, and also the design section geometry. We can look at column forces, wall reactions, support reactions, the punching shear design. We can show the punching shear stress check results. We'll go ahead and open that report. Here we show the stress ratios for each column, the condition, the factored shear and moment used for the design, the stresses versus allowable. That can be done for each strength combination. Under punching shear, we can also look at the stress check parameters and also any reinforcement that's necessary for the design. We can include skip patterns in the modeling, which we have not done for this model, and then we get into quantity and cost with tendon and rebar totals. To expedite the creation of a report, we can go to Reports, Compiled Reports. We can select any number of individual reports from the left-hand side, move those to the right-hand side where changes can be made by deleting or rearranging. If changes are made to this side, we'll go to File and we'll regenerate the report, after which the report can be printed or viewed. Once the user has determined that the reinforcement is satisfactory, after any changes or modifications have been made, he or she can again export using the File, Export to DWG or DXF command. You can also print the screen by selecting the print option within the program. This will complete the tutorial of how to apply MAT 2009 to a specific design project.